read the problem funny. Okay, let's go ahead and get started today. Look at this one. Okay, the test went really well. Went very, very well. Everybody. I know one group is kind of but that's okay. The grades are going to be fine at the end of when this is all said and done. So, you got to remember, you've only been doing this stuff for about 10 days or so, and it's hard stuff. And we're going to move on. And I think I said that we may not have a test every week, but I would like to just cover Chapter 20 today and Monday, and then just do a regroup again and do a test again just over Chapter 20 too, okay? And then we will do a test over Chapters 21 and 22. Chapter 23, I might give you a little bit of class on, but for the most part, I'll let the lab handle that one, just because it's kind of esoteric type stuff. I mean, it's good stuff, but there's other stuff I'd rather you learn about, like special relativity and fun stuff like that. Okay, so without further ado, let's go ahead and launch into today's class. And here's what we're going to do. Here's a new symbol that you need to know about, and a new picture that you may or may not have seen before. Is Mr. Lucchese? Yeah, Mr. Lucchese's here. He's played with circuits before, so he's probably seen these drawings. All right, here's squiggly line. I'm going to draw a circuit here. What is that? You have no idea. A resistor. Okay. What is that? That's the battery or a voltage place, right? And later on, you'll see this too. That means that's an AC. This is DC for direct current. This is AC for alternating current, okay? All right, so, and by convention, here's the deal. Now, here's the deal. What flows in a wire? Is it the protons or the electrons? The electrons. You've all had your chemistry. You all know a little bit of the quantum mechanics of that. You have these free electrons in that soupy cloud around the copper. And so it's the electrons that actually flow and bang into each other and make current. But you know what? Ben Franklin said it was the protons. It's the positive guys moving around. Okay? And so by convention, so get used to that phrase. From now on, when I say by convention, we know that this is going to go, we draw it this way for I, for the current. All right, now, something I think we should do before we go any further is take a quick review, because this is a lot of new stuff, a lot of terminology. Okay, when you see this, that's a Q. What are we talking about? And it's measured in coulombs. Coulombs. Okay, and that's how we measure charge. And it can be quantized because we can't get any smaller than 1.6 times 10 to the negative 19. What's another thing we saw? F, good old force. We know that's newtons. Okay? E. How do we measure the electric field? What units? Newtons per coulomb, or you can do newtons per coulomb because you get F over Q. Oh, so it's newtons per coulomb. What's another one? It's a way to do it. Newtons per coulomb. You could also do it as volts per meter. No. Yeah. Yeah, because you could do it as volts per meter. Yep. Okay, but for the most part, we call it newtons per coulomb. It doesn't have a fancy word. It doesn't have a name. Like this has coulombs. This has newtons. When we have V, what is this called? Volts. And what is this? Joules per coulomb. Joules per coulomb. Okay. Okay, yeah, and this is also volts per meter. I had to write this one out because if I put joules per coulomb per volt, what do I get? I get joules, which is equivalent to Newton meter divided by coulomb per meter. And I wind up with those cancel. I wind up, what did I do here? So I wind up with newtons per coulomb. What's that? Oh, that's an electric field. Yeah. There we go. So this is volts per meter, and this is good. Newtons per coulomb. Whoa. All right. Yeah, you can get a headache from all this. Okay, what else did we say? So far we've got electric field, voltage, or potential as we call it, and coulombs, and that's pretty much 18 and 19. We had one other little thing in there, though. The favorite thing that we always like to teach with, the capacitance. Parallel plate capacitance, and we found out that capacitance is equal to Q times C, and capacitance is measured in what? Remember? Farads, right. Farads. Okay? That's measured in farads after probably the father of electricity and magnetism. Well, there's several. There's Maxwell, there's Faraday, and there's a whole bunch of them. So I wanted to make sure we had a good discussion, and we're going to start getting into this thing today. Okay? And it goes pretty quick. It's nice, straightforward algebra stuff, and it's actually kind of nice and simple. Relative. Remember, simple is relative. All right, so here we go. Let's start off with this. Charge. Way back in the beginning, a whole 9 days ago, or 13 days ago, how did we say we measured charge? In coulombs, but we do it by what? How would we find the charge? If we knew the number of electrons, right, or protons, and multiplied them by the charge, we'd find the total charge. Equals NE. Okay? Equals NE. Now, and so that's charge being placed on something. Let's see how fast it's being placed. And so we divide this by time. Take our charge and divide it by time. Okay? I had a point to this. So the total charge divided by time. So basically what they tell you is dq times dt is equal to I. And those are good old amps. Okay? That's how much current is flowing per second. And as some of you found, one of the things I do like about the new physics books is they use real numbers. They use real data. And as some of you found on the test, you're like, wow, we generate 9,000 volts. Sometimes you generate up to 40,000 volts when you're walking across a carpet with socks on. Okay? But the thing is, what keeps you from dying when you touch the doorknob is that the amps are so small. There's not much charge there. I mean, there's definitely a difference in the positive and negative charge. You're all negative and this is all positive, so there's a difference of 40,000 volts, possibly, but the amount of amps isn't, the amount of coulombs isn't that great. So the amount of amps or charge of amps that are going to flow in a split second, really a split second, is very, very small. So that's why it just kind of bites a little bit, or maybe doesn't even, you can't feel it at all. Okay, so that's the way we measure current. Current is the change in coulombs divided by the change in time. Okay? Now, all right. I'll get away from it. I don't need these right now. Thought I did, but I don't. Okay, not yet. Now, we put up this guy, this resistance thing here, okay? And here's how you measure resistance. Basically, here's what resistance is. It depends, resistance in a wire depends on the material that's made. Good conductors, and so have a very high resistivity. This rho, which we call resistivity. And those are all being found by experiment in labs with chemists and physicists working together to find out what the resistivity of certain things, of certain materials are. And so you get R, which is a resistance, equals the resistivity of the material times the length of the material divided by the cross-sectional area. So here we go. Let's do a laser light show here real quick. No. No, it doesn't. There you go. Right. Yeah. There you go. Isn't that fun? Did that... James, did that come on?
No.
No. Now?
No. Yes.
Okay. We're going to go to my favorite little web page, the FET, and one reason I came in early was so I could build these pictures and get the things I wanted you to see real quick. It takes care of all their examples. I think a computer simulation is worth 1,000 words sometimes. So here we go. Well, let's go ahead and turn it all off. Okay, now, what we're going to show here is resistance in a wire. There it is. R equals rho times L over A, where L is the length of the wire. So let's see if we got wood, which is going to have a real high resistivity. There's a table for the resistivities in your book. Let's see if we had wood. So we'd raise this toggle up. What happens to the resistance? It goes way high, right? And so that means the charge can't flow through. It's resisting the charge. It's the dam, basically. It's resisting the flow of the electrons. It's resisting the current. So if you lower that, okay. Now then, let's get it nice and normal. Let's have a low resistivity like we have in copper, okay. Has a pretty low resistivity. But let's take, let's say, what happens to the resistivity if we increase the length? What would happen to the resistivity if we increase the length? Would it go up or down? Up. So we increase the length, resistivity goes up a little bit. Think about that. What happens if we increase or decrease the cross-sectional area? What happens to the resistivity? If we increase the area, yeah, the resistance decreases. If we lower it, if we make the cross-sectional area smaller, then the resistivity increases. This is why. So let's take a look at this. Now, resistance is hot. Basically what resistance is, see how they've put the little micro particles in here? Basically what resistance is it's how much the electrons, those free electrons, bang into each other when they're feeling an electromotive force and they're moving. Okay, it's how much they bang into each other. It's like a big Ramones concert. It's a mosh pit. in there, okay? And if the resistance is low, you guys are too young to remember the Ramones, but anyway, if the resistance is, oh, I'm not supposed to point with that. Let me come over here. And I'm supposed to turn this on too, aren't I? Whatever. They're like, whatever. Okay. So anyway, if the resistance is high, it gets, just like in a mosh pit, it gets hot. Okay? Things get hot. All right? And so if you've got a really thin gauge wire that needs a lot of amps that's hooked up to a space heater, and you got a real thin extension cord, look what happens when that thin, because it's got low area, the resistance goes up. It gets very, very hot. Okay? That's why those small extension cords are dangerous with space heaters, because they'll eventually melt the coating on the outside of it, the plastic insulator on the outside of it, and then start a fire. Okay? All right. So there you go. Got that part done. Okay. Now we'll turn that off. We'll go back to that here in a minute, too. Okay, so now you know what resistance is. You've seen how it works. R equals rho times the length of the wire over A. But I think what's more important is you have a conceptual understanding of what resistance is that's going on inside the wire. Now you are ready for your yoga lesson in electricity. We're going to do Ohm's Law. You get it? Okay. Ohm. Here it is. Ooh, new symbol. You know what that is? That's this voltage. That's for the history of taking what we call the electromotive force. The electromotive force. In other words, let's say we're a wire. We're the wire. We're the electrons on that wire. And in that back wall becomes, they put the back end of a battery there, the negative end of a battery there, and then the rest of this wire is attached to the positive terminal of the battery. Put a big negative in there. What do we do? What are we going to do? We're going to start running this way. Is that voltage really a force, though? No, it's not really a force. But back in the old days, back in the 17 and 1800s, when they were first figuring this out, they called it an electromotive force because they noticed that it moved charge. Okay, so E, which is also V. All right, so sometimes we'll write it with a fancy E. Sometimes we'll write it with a V for voltage. It's the same thing. Equals the current times the resistance. And we are going to play with this all day long for all of chapter 20. V equals IR. It's Ohm's Law. It's huge. It shows up so there's all kinds of ways, you can write then I equals R over V. You can write R equals V over I. You can massage that any way that you want. Okay? So V equals IR. So let's do an example of that real quick. I'll show you some other things. Some of you who might be following along at home have noticed that I've jumped from, I did resistivity and resistance because out of order, because they jumped into Ohm's Law, the book did, without explaining to you what resistance was. All right. So now, in other words, the voltage I have here, this voltage that I have here equals this resistance times this current. That's what we're saying. Okay? All right. So now, a flashlight. what do we measure a flashlight in? Which is power. Which is power. And what is power? What?
Joules per second.
There we go. Joules per second, right? So let's tie all this together. So you get power is equal to joules per second. Okay? Now, if power is joules per second, something that drove you all crazy when you're trying to find that EPE, the electric potential energy, how do we measure the electric potential energy? It's measured in joules. But how did we get it when we were doing electricity? Remember? EPE equals
Negative work divided by the charge.
negative work divided by the charge, also known as, okay, the work. Negative work divided by the charge, that's the voltage. You're giving me the voltage. What's work then? Remember? It's QV. Coulombs times volts, right? All right, so you got joules per second equals coulombs times volts. Remember you had QV? Oh, that's GV. That's gravity times voltage. That's a flux capacitor. In other words, it doesn't exist. All right, there's QV, all right, which is energy, divided by seconds. What's coulombs per second? Oh, we don't have it up there anymore. Remember what coulombs per second was? Yes, which is measured as I. So power equals IV. Okay, so P equals IV. So we've got V equals IR and power equals IV. And we're going to do some examples here. P equals IR and P equals IV and V equals IR. So we can also write power this way. Since I is equal to R over V, it's all right.
V over R.
Yeah. Why'd y'all let me do that? It's out there. That mistake is out there for millions to see. Okay. So if I is equal to V over R, I can plug that V over R in here times V. And so here's a variation on the theme. V squared over R. I can also say, well, power is equal to V over I, or I. What am I doing? Can I not do algebra today?
I squared R.
Yes, that's what I'm trying to make. Oh, V equals IR. There we go. Whew. Thank you. Bailing me out there. Playing without a net here. I don't have my notes right next to me. Okay, so P equals I squared R. So it's either amperage squared times R or V squared or the voltage squared divided by R. Okay? All right. So let's do some of the examples that they have in the book. There. Believe it or not, we've covered like a good third of chapter 20 already. Good third of it. And we'll finish. I didn't think we'd get to it, but we are going to get to AC current. I could go on to that, but I'm not going to right now. I'm going to do some examples in the book. And I'm going to make your homework problems that'll be due like Wednesday off chapter 20. Very straightforward, the first half of chapter 20. And I mean, you're just going to be doing a little algebra like this all day long. It's a little algebra thing, okay? All right. It's not going to be that bad. But first you need to have a few problems modeled for you. So here we go. let's say this. It says a battery pack of a pocket calculator has a voltage of 3 volts and delivers a current of 0.17 milliamps. So the battery pack, which would be 2 batteries kind of put like this, end to end. And by the way, so this would be like 1.5 and this is 1.5. By the way, here's something kind of cool I looked up in Scientific American. Y'all heard of electric eels? It's a very true thing. It's a very real thing. And basically what the scientists have found out, what biologists have found out, working with biophysicists probably, and chemists and all that stuff, very interdisciplinary biology is, what they found out with electric eels is along their spine, they have these specialized cells that when they're not upset or they're not hungry and they're not hunting are just like little batteries that are all discombobulated, just kind of laid out. You know, just like you take these batteries and they're just kind of laid out. But when they get excited and they get upset, or when they're on the hunt and they bite something, those cells get in line and work just like a battery pack on there's an enzyme that they secrete that lines up that electric charge, and they set themselves up. They're an open circuit, and then when they close their mouth on something, they close the circuit, and boom. That's how they shock things. Or when you touch them, you close the circuit if you touch them anywhere near the spine. So isn't that weird? Anyway, so that's how electric eels work. Now, that would be the only thing you remember from the whole lecture, but that's okay. All right, and the current inside this little thing, the current is 0.17 milliamps. Now, milli would be 0.17 times 10 to the negative 3 amps. Okay? And it says, how much charge flows in the circuit and how much energy does the battery deliver to the calculator circuit? Okay. What did we say energy was again? Coulombs times volts. So we need the charge. We need how much charge? Okay? Oh, and 1 hour of operation. There you go. T equals 1 hour. I was going to say, I'm stuck. Help me out here. But I was going, I needed time. So that'd be 3,600 seconds. How much charge flows in 3,600 seconds? Well, let's see. We've got I equals Q over T, the change in the charge from 0 to whatever, divided by delta T. So we get Q equals I times delta T. And so we get 0.17 times 10 to the negative 3 times 3,600. And the amount of charge then is equal to 0.61 coulombs. Okay. And then they said, well, how much energy is that? So they want the EPE. How much electric potential energy has been used up? And so the EPE, again, is QV. So that'd be delta Q times the V. You just multiply that by 3, 1.8 joules. Okay. And then a question could be, we could come back full circle and say, well, how many watts of power was used? By the way, on your electric bill, how many of you pay your electric bill? Okay. I don't. My wife does. Okay. How does your electric bill come? What's it come in? Kilowatt hours. So it's kilowatt joules times a time. If I take joules times a time, then the thing cancels. So that's why kilowatt hours is a measurement of energy. Okay. Right. So they are measuring how much energy you're using. Okay. All right. Let's look at another example. Let's try and use Ohm's Law here. Oh, this is good. This will be a good one. So your homework problems will be like this. Emily's going, got it. I can do it. All right. Good. All right, now. The filament in a light bulb is a resistor. Okay, filament in a light bulb is a resistor. It gets very, very hot, and so it burns red hot light and a thin piece of wire, tungsten, actually. And the wire becomes hot enough to emit light because of the current in it. Okay, all right, and so you got a simple that one little current circuit that I drew up here was an example of a flashlight battery. Okay, a flashlight that uses 3 volts provides a current of 0.4 amps in the filament. Determine the resistance of the glowing filament. All right, so we're going to determine the resistance of the glowing filament. We have this. We've got V equals 3.0 volts. We've got I equals 0.4 amps. Okay? And now we need R. We need the resistance. So we get this. We get I equals, V equals IR. So V over I, did I do it right this time? Equals R. I'm gun shy now. So I get 3 divided by 4, so that's about 7.5. So I get 3.0 divided by 0.4, and that equals 7.5. Oh, ohms. Here it is. Resistance, they all pledge to the omegas. They're omegas. All right? That's one of the harder things that's one of the things that I think makes learning E&M in a very fast time difficult because there's so many new terms. Ohms, resistance, voltage, power, watts, joules per second. Boy, there's just all kinds of stuff going on. Okay. Now, kind of an interesting problem that I might ask you to do, just because I think it's good for you, is in the book, there's a problem that talks about resistance and resistivity, and it says like the filament in an incandescent light bulb is made from tungsten, and so you'd have to look up the resistivity of tungsten, and the light bulb is plugged into a 120 volt outlet and draws a current of 1.24 amps. If the radius of the tungsten wire is so many millimeters, how long must the wire be? Does that make sense? In other words, you're given the voltage, you're given V, you're given I, and you're given rho, because you can look that up, and you're given the radius. So you're given A, which is pi r squared. You're given all that. Can you figure out L from this? Yeah, because you got V equals IR and R equals rho times L over A. Okay? So it's right there. What's that? That would be problem 18. Just so you get kind of used to doing that kind of thing. Or problem 7, I like the problem 7, the resistance of a bagel toaster. Y'all know what a bagel toaster is? Well, if you're in the South, it's where you put your dog after a coon hunt to get him warm. Kidding. That was, oh man, it's going out to millions now. Bagel, beagle. All right. Boy, that was bad. Now, I wait every semester to crack that joke, and every semester it kind of goes over like that. You'd think I'd learn. All right. Okay, so let's look at a power problem then. Let's look at a power problem. So what we've learned so far is this. We know that I is equal to the change in Q over the change in T. We've learned that resistance is equal to the resistivity, depending on the material, as a length divided by the area. And one of the things that I learned, practical knowledge, is that here's something. Those of you who've done home repair and things like that and have hung out with electricians, don't answer this. But for those of you who haven't, like me, which is thicker, 20 gauge wire or 16 gauge wire? 16 gauge wire is thicker, okay? And the reason is because it's like, have any of you ever seen those spaghetti measurers before with the little circles? Now, how many strands of, well, no, that destroys my argument. Oh, here we go. In other words, to take that wire, all right, so if we take this guy, it's the reverse of that, actually. If I had this rate, if I had a circle this size, and I have a thick wire going through that little circle, there's going to be fewer of them than a thin wire. Okay? And so that's why if only 16 wires fits through here, then it must be thicker, right? Than 20 strands. Okay, good. All right. So let's look at power. Then I got a laser light show to show you again. And should be good. All right. Let's look at their example for power. Okay. Power, they say this. In a flashlight, oh, okay, and we're back to our flashlight. The current is 0.4 amps, and the voltage is 3 volts. The power delivered to the bulb, we want to find the power delivered to the bulb and the electric energy dissipated in the bulb in 5.5 minutes of operation. Okay? So if we find power, here's another relationship I want you to get used to. So we've gotten this, V equals IR. We also know that P equals IV. One thing I want you to get used to seeing too is PT equals energy. Power times time is equal to energy. Okay? So you can also kind of play off this and go PT equals QV. Then we're back to right where I started again. P equals Q over T times V. Q over T is I. We're back right where we started with IV. Okay? All right. So let's go. So with that in mind, let's go through this. It says the voltage is 3. Oh, find the power. Well, if we know voltage and amperage, power is pretty easy. P equals 0.4 amps times 3 volts. That should be 1.2 watts. Okay? And the energy that it used? Now, a sneaky, slimy question that could be asked on a take-home test was, how much charge moved through there while it was in operation? Could we figure that out if we had the minutes? Could we find out the number? If you were told the power, could you work it backwards? 1.2 watts of power? Okay. All right, so anyway, so the energy is going to equal P times T, and they gave us that the time was 5.5 minutes, which would be 330 seconds. So equals 1.2 watts times 330 seconds. Which is 400 joules, roughly. Joules. And we'd know this, so we'd know how much charge went through there. We could find the number, we could find the charge. Q, V is equal to 400. We know the voltage, so Q is equal to 400 divided by 3, which is 133, 133.3 coulombs. Wow. That's a lot of coulombs going through there in 5.5 minutes. So we could also figure out the charge. We could also find the number. Then the number of electrons, divide that by 1.6 times 10 to the negative 19, and you get the number of electrons that actually went through there. But it seems like a lot. That's huge, because when we talked about it, that's like 10 bolts of lightning going through that thing. But it's in 5.5 minutes. That's a long time for things moving close to the speed of light to accumulate. Okay? All right, good. Now, so let's take a look at some things here so that you get ready for Monday. And then I'll talk about alternating current from about 7 to 1 until 1 o'clock. Hopefully, I'm going to the Keystone Cops tonight, also known as the Kansas City Royals. And hopefully it won't rain. I'd hate for it to rain out my T-ball game where they play defense. All right, now, poor Royals. But actually, people say, oh, the poor Royals. I have a hard time. You know what? What's that?
You cannot feel that.
No. And well,
They might be watching.
typing Melissa speaks again.
Sorry.
Right. But you really can't feel sorry for people. You know what the Major League Baseball, the guy sitting on the bench, you know how much he's making who never gets in a game? The league minimum, which is? He's making $250K for just going to the ballpark every day and doing what he loves to do. That's why when people say, poor Tony Gonzalez. I do not feel sorry for any, he never made a championship. Who cares? He makes $11 million a year. Wah, go to Atlanta. See ya. All right, anyway. So, I don't know how I get off on these things. But anyway, here we go. First of all, let's take a look at here we go. Here it is. Here's just a regular old circuit flowing. Okay, and I built this circuit already. Watch what happens if I take the resistance out. If I take all the, here I've got to show the value of the resistance. It's at 10 ohms. Show the value of this resistance. It's at 26 ohms. Okay. And I wonder what the voltage is. So what we'll do is we'll put this guy on the positive end, put this guy on the negative end, see how much charge is flowing. 18 volts between the positive and the negative. All right. Now, here's what we're getting up to here. And so if he's 18 volts, and these resistance, what's the total resistance here? 36. These guys are what is known as in series right now. They're in series resistance. And so let's see something here. The amps is 0.5. Okay. All right. Now, since they're kind of upside down to this one, I'll put this here. The negative goes there. That goes there. What's he? Negative 13. What do you think the voltage is over here? All right, let's try this again. He's positive 18. This guy becomes, what was that?
Negative.
It'll be a negative 5. If I configure it the exact same, if I keep my configuration uniform, where I put the black where it's flowing out. Okay, he's negative 5. 18 plus negative 13 plus negative 5 equals what? 0. So the voltage stays the same. Okay, so the voltage is constant. This is how we start building circuits. Okay, and you can put these guys in parallel too, which is different. They're in series right now. When they go to parallel, I'll show you how to do that too. So that's what we're getting to. Let's talk real quick. And so if I pump up the volume here, change voltage. Let's wrap it up. So if I increase the voltage, what's going to happen to those little blue arrows of current flowing through there? Or blue balls? Yeah. Or blue spheres, let's say. Okay. Not that many. All right. So there you go. Yeah, so yeah, if I increase the voltage, I'm trying to pump those things up. And here's kind of a cool thing on this thing too, is they show us how a battery works a little bit. I just thought they were magic. But I just thought they were magic. And they kind of show it as magic too. They kind of, in this thing, they kind of make it, you know, they go to the Kansas science standards. But anyway, kidding. All right, so we want to decide, so these guys are a chemical reaction, these little men. So, desired voltage, I want all my electrons moved over here. So I'm going to pump up the volume. Oh, the other way, yeah. So they bring it over here. There they go. Now if I want higher voltage, I want them to go get some more charge. There they go. They go get some more charge, bring it over. What's that? It's disturbing? It's chemistry. You guys are all chemistry majors. There it is. So, but now let's change it. We want to change it.
So to answer this question, when it's asked how does battery work, we can say little men.
Yeah, little men move the charge. That's why we physicists answer chemistry questions. Oh, it's little green men. Do it. Let's do the chemical reaction. Those guys are just those guys are enzymes. Making a chemical reaction, right? Is that right? Isn't that what enzymes do? Maybe? I don't know. I haven't had chemistry since I took high school chemistry from Mr. Stevie. Okay. It's a big hole in my education. All right. Have we looked at all my cool stuff? Yeah, we looked at that. So if I increase the resistance, oh, we didn't look at this. Increase the resistance. I goes down. Increase the voltage. Bloop, bloop. Okay. All that. Okay, now let's talk real quick about, just so that we can say, we finished half the chapter today. Hope we didn't go too fast, but it's all relatively straightforward. It's much easier than all that voltage and EPE and things out at infinity and you bring it in and put it on a triangle stuff, right? This is nice, straightforward things. Okay. All right. We'll go ahead and turn off the projector. Off the projector. There we go. All right. Okay, now then. What kind of current is powering these lights? AC or DC? AC. We are an AC nation, okay? And in fact, for power to work, there is a Croatian man named Nikola Tesla who immigrated to America, and he was a contemporary of Thomas Edison's. And he was very interested in how to get all this power to move from one place to another. How can we power, this was back when most homes still had little oil lamps and everything that were powered by, luckily for the whale population, oil was found in the early 1800s and stuff like that. And so the whaling industry dropped off because we didn't need that oil for our lamps anymore. But anyway, most houses were powered by oil. But we have this powerful thing, this electricity. How do we get it to move from one house to another and everything else? Well, DC current doesn't travel very far. Einstein, and I'm going to bring in my friend Mike Kelly, who is an adjunct. He's retired from Kansas City Power and Light, and so he loves teaching the power section to the electrical engineers here. So he teaches the whole power package. He's got this neat display, and he explains where Edison ran into trouble. Because Edison, here's what Edison wanted. He wanted DC current everywhere because he thought AC current was too dangerous because the voltage goes way high. Right? You get like Kansas City Power and Light puts out 1,000,000 volts or something like that. And as long as the amperage is low, that's okay. It's not that dangerous unless you're the poor squirrel who runs into the transformer box. Then it is. Right? But anyway, Tesla, Nikola Tesla, and we'll get to Tesla with the magnetic fields and everything, said, oh no, we need AC current because AC, working with a magnetic field, which we'll get to in chapters 21 and 22, we can transfer this power long distances. Edison's vision was he wanted, like on every block, every city block, he wanted a little power station that would pump out DC current. And Tesla said, no, let's have one central power station that pumps it out to thousands of homes. Okay? And, of course, that's what we have. Because the thing is, we can control with transformers, which we'll learn about, and capacitors, which you know a little bit about, we can control the current, and you can project it over hundreds and thousands of miles. And, in fact, my friend Mike will show you the grid of the United States. Okay? And it's kind of cool stuff. All right. And I asked him, and it gets complicated, because how does California sell its power to North Dakota? They can. They can transfer the power. They can say, well, we got too much here, you buy it, and stuff like that. It's weird. There you go. That's the physicist answering the chemistry question. Right. It's magic. All right. Anyway, so let's take a look at alternating current real quick. Now, alternating means it goes back and forth with a frequency. Boom, 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 boom. Anybody know what the frequency is that we have?
117.
What?
117 RMS.
Oh, for what?
For the outlet.
For the voltage? Oh! Here's what John's doing. He's messing with me. He's saying the root mean squared. The voltage of the root mean squared is, he's saying it's about 117. Okay? All right. I was just going to go with regular voltage 110. I want the frequency. Give me the freaks. What's the frequency that it's bouncing back and forth? How fast is it? How many times a second is it bouncing back and forth? Do you all know? Yeah, 60. That's what I was asking that one. See, he builds circuits. Are you like a radio head or something? Or
No.
Oh, okay. All right. Anyway, so it's 60 hertz. 60 times a second. All right? And so since it's bouncing back and forth, what does that mean? If I'm going like, boom, here's my positive now, but I'm doing the positive, 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 like this, but I'm doing that 60 times a second. Okay, so that means I'm changing. So my voltage has got to be, so when it's like this, okay, so it's going down, it's going up and down, it's going positive, negative all the time. So what nice little mathematical function do we have that goes up and down but stays within a confined area? The sine. Yes. So this is at time. This is our time down here. This is at t equals 0. And this is our voltage. This is when we're at plus. This is when we're at minus. And here's what John was talking about. It's going to have, your voltage is going to go bounce back and forth like this. Okay? Your voltage is going to go back and forth like this. And he's saying if you take the average, what they call the root mean square of all those voltages, you wind up with this. That's what he's talking about. Okay? Now, in our book, we don't deal with the voltage root mean square. we deal with the amperage and the resistance. Okay? No, I'm sorry. We do deal with the voltage, the VRMS. We sure do. We sure do. Okay. Now in Europe, they bounce back and forth a little bit faster. But here's what the equation looks like. So you get voltage is equal to V naught, which is the 110, or the 120 that they say. V naught times the sine of 2 pi times the frequency times the time. So we hold the frequency at 60, and then at different, so whenever we get a multiple of, what is the sine of 2 pi? Well, yeah, it's 0. So whenever this phrase right here comes out to be a multiple of 2 pi, we get 0. Whenever it comes out to be a multiple of pi over 2, we get 1. Whenever it comes out to be a multiple of pi over negative 2, we get negative 1. So here it is at 3 pi over 2. Here it is at pi over 2. It's at a max this way. And then this is plus, minus. What's it down here? Minus, plus. Plus, minus, minus, plus. Okay? And so we get this. So the average power, what did we say power was? What's the equation? Y'all learned it 25 minutes ago? You should have it. Yes, power equals IV. You should have it memorized. Now, we're going to talk about, as John was saying, since we got this VRMS, we're going to talk about the average power. Okay? Since power equals IV, notice what's happening here with V. It's going between positive and negative. Okay? But when the voltage is negative, guess what? So is the amperage. Now you're going, wait a minute, negative amperage? Yeah, because it's fluctuating too. Okay? So you get negative times negative, so the power is always positive. But it fluctuates from 0 to a big number. Okay? And so we take the average power is actually equal to 1/2 of the largest amperage times the largest voltage. Okay? Now then, yes. And so now, this is the same thing as, okay, we're going to throw some algebraic fairy dust on here at the end of Friday. Whoosh, throw it on there. Does that make sense? Is that still the same thing? Because if I take the square root of 2 times square root of 2, what do I get? 2. So I still got 2 in the denominator. Equals, and we call those guys IRMS, root mean squared, and VRMS. Okay? So IRMS, and this is just in general. John is giving us like real world when you got to really work with it. I'm giving you kind of theoretical type stuff here. It's close. So the IRMS is equal to IO divided by the square root of 2. VRMS is equal to VO times the square root of 2. And remember, IO is not the initial, it's the maximum. Anytime you see the not there, it means maximum. Okay? I think your heads should hurt enough as it is. And then all the other power things still apply. All the other equations for power still apply. So we still have equals VRMS squared over R. Notice, the resistance is always the same. He never changes. He's not variable. Okay? One last one, David. Then we got it. Then we'll be done. Equals IRMS squared times R. I squared R. There you go. All right. I don't know what you got out of that, but we got most of chapter. Now, the rest of chapter 20 is kind of fun. All righty.
Reading the chart, that's specking?
No. You can designate a fearless leader to hold on to it, or you can go make copies of it, or